Observe. No!
Today we're going to be looking at a couple of ElectroBOOM videos, starting with AC versus DC, and this one's specifically on how it is received by the body. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
One of the common questions is that what kind of electricity hurts more? AC, alternating current, or DC, direct current? So I'm going to measure the electricity pain level on a human's body, which is myself. But first, let's measure the resistance of the skin on tongue and fingers for reference.
Really? The tongue? Dude. So I wouldn't know from experimenting from first-hand experience, but how I would guess would be AC would have more sensation just because it oscillates at 60 hertz frequency or something similar, depending on where you live. 60 in the US. But anyway, it's a more rhythmic pattern, which, yeah, that's going to stimulate some nerves. Muscles being seized up, compared to DC, where it's constant. So a single sustained contraction, sharper at the point of contact, but none of this back and forth. So less of an exercise on someone's nerve system, but I certainly wouldn't underestimate DC in that category. But those are my thoughts. Let's see what actually happens.
So first, let's measure the resistance of dry skin. It's 600K and above. Now if I wet my fingers with my
That tracks. That's consistent with what I learned in my electrical safety procedures.
saliva,
Goes to like 1,000.
you can see it's 100K and above. If I measure the resistance of
with saliva. Okay. So not soaking wet. Yeah, that makes more sense.
my tongue, it's 10K, 20K and above. So the resistance of the tongue is at least 30 times less than the dry skin, and it will feel the electricity at much lower levels, and for that reason I'll apply electricity to my tongue. I should
Okay. Never seen this in any safety training. All right.
tell you, I've accidentally zapped myself in the past many times and I kind of know what I'm dealing with.
Accidentally versus on purpose. All right.
So you better trust me on this one and don't hurt yourselves. If you really want to know what electricity pain feels like, then take a 9 volt or less battery and put it on your tongue and you'll know. As I mentioned in my other
That'll be DC.
video, a power supply like this one that can generate 70 amps doesn't necessarily hurt you at all if the voltage is set very low. Observe. No!
Did you mean on your tongue or on your skin?
The hell set this to 25 volts?
Oh, dude.
Before using a power supply, always make sure its level is set properly.
What was that supposed to be, 1? Oh. What he's doing is a great exercise in teaching operators to always verify their conditions, verify everything is set up properly before you start a process. Whether it be starting up a nuclear power plant, whether it be putting a chem feed skid on research, or any task. It's a fundamental that is drilled into training, especially at nuclear power plants, though I'd imagine some level of it at any industrial facility. And you talk about the hazards, whether it's electrical, whether it's chemical, whether it's radiological, whether it's thermal. Yep.
Let's try again, and this time I start from 1 volt, and I'll watch for 4 levels.
Yeah.
When I start sensing electricity, when it becomes annoying, when it feels like torture, and when I can't raise it anymore.
I sure hope someone else is holding the camera or is in the vicinity ready to assist, because that is one, especially if you're doing something, you don't want to do this task alone. Now, I know he's working with lower voltages, but still.
Here we go. I barely feel it at 1 volt.
And he's doing one hand and he's not having a buddy like operate while he, wow.
At around 5 volt, it's kind of annoying.
He's still...
Yeah, I would say around 9 volt, it feels like torture. Although if you want to torture someone and make them talk, you probably don't want to hurt their tongue. And besides, you should never torture each other.
There you go, it's like, okay. This is all education here.
Always remember, people in the first world countries never torture anybody. They always hire the third world countries to do the job. Unless, of course, if you're married.
Wow. That's okay.
That's it. I can't really go over 12 volts. I should say that women's pain threshold is higher than men, so they should be able to go to higher levels. Now let's try AC. I've heard that human body has some
Oh, I thought he was about to test that. Okay.
capacitive properties, meaning that it will let AC through easier than DC. So I expect AC to hurt more at lower
That's
levels,
also true.
and also it will hurt more at higher frequencies. But before that, let me show you something. I've set the signal generator to 5 Hz, 7 volt RMS.
Okay.
Let me change the frequency now.
What'd you change it to? Oh yeah, it's causing it to cease
Nice.
up.
By the way, I can do this too. Now let's reduce
Yes. If you don't know how to do that, all you got to do is run some AC voltage through your tongue, then you figure out how. Okay.
the voltage level and increase the frequency all the way to 60 Hz. I shock my ass sitting on these live wires. Always clean up those
Oh my goodness. Just no.
otherwise something will bite you in the ass. Okay, AC is starting
Brings up the live wire things at enough to cause this sort of reaction, but not enough to cause serious injury. Wow.
at 1 volt. Huh?
It really does take a certain level of expertise to do it enough that it can be silly, scarier than it looks, or even comical without it getting serious. So that's a lot of skill on ElectroBOOM's part here.
I can definitely feel it now. It's quite annoying at 3.5 volts. Oh,
Yeah, that's a lower voltage from the DC one.
it's torturing at 4.5 volt. Oh,
Just why the tongue? I mean, he can use lesser voltage but to create more of an effect, but why?
that's it. I can't really go over 6.5 volts.
What's the aftertaste like?
So it was confirmed. According to my senses, the AC hurts at RMS levels half of the DC level. Anything for science.
Oh, I see what he did there. Hertz is in the measurement of frequency. Okay, that's pretty clever. Oh, man. All right, related. Now we're going to look at Edison's DC versus Tesla's AC and why AC is mainly used at home. Well, it's easier to generate a lot more at AC. Can you imagine a nuclear power plant with an output that's DC?
Hi, why do we ever use AC to power homes instead of DC? Haven't I showed you that AC is typically more dangerous than DC? Can we run everything on DC? Yes. In fact, pretty much every device at home has to rectify AC into DC first before it can use it. So why?
Well, DC would be extremely expensive over long-range transmission lines. So high voltage DC does exist, but it requires a lot of more complicated equipment to convert, not to mention transporting hundreds of miles away from the nuclear power plant that's powering your home. You're going to get, the line losses are going to be a lot less with AC. Because out of a nuclear power plant, the main generator is about 25,000 volts. At the plant I worked at, it was stepped up to 345,000 volts for long-range transmission. And that gets stepped down into substations and to street transformers and brings that all the way down to 120 volts in the US. Anyway, it's a little different depending on where you live, but those conversions are more expensive and you want the high voltage for long-range transmission. Or build a low-voltage nuclear power plant in someone's house. Somehow.
Why am I angry? The reason is elementary. Once there was a fight between a guy named Nikola Tesla being AC and Thomas Edison being DC, and Tesla won the contract for his employer Westinghouse Company to provide power with AC. No matter how hard Thomas Edison tried to expose the dangerous nature of AC by electrocuting dogs and elephants in public. Wow. Now I remember why I'm angry. This Edison guy was an animal. He even invented the electric chair to execute with AC. Not because it was a cleaner or better way to execute, because he wanted to deface AC by forever associating it with death.
As someone who works in nuclear power, I can kind of relate, because a lot of people are afraid of something that they think is dangerous, even though it's not in the right hands anyway. And it's really just a matter of having respect for your energy source and using the appropriate amount of safety systems that are in place, just like you would for AC power. And of course, nuclear power is designed to produce AC power, so it obviously works hand in hand. But I knew somewhat about the feud between Tesla and Edison, but I didn't realize it went into saying one is more dangerous than the other.
Nikola Tesla very rightfully won this battle. Yes, AC can be more dangerous than the same level DC, but a higher level DC can be as dangerous, if not more. And just because something is dangerous, we don't stop using them. Like, for example, if you live in a high-rise, you're not in a constant risk of jumping off the window.
That's a good point. And higher energy doesn't necessarily mean something is dangerous. At a nuclear power plant, the situation where you're the most vulnerable is at low power. I'm not just talking about Chernobyl. I know that reactor design was straight up unstable at low power. But when you're at low power, the reactor responds more coarsely to changes in control rod position, for instance. That is to say, if you want to raise power, when you're at 10% power, withdrawing control rods one step is going to have a larger effect than withdrawing control rods one step at 95% power, for instance. So it's not dangerous. It's not even difficult to control. It's just more coarse. So you can argue that the risk profile is higher than it is normally. And that's also to say piping, valves, coolant systems, everything is designed at a nuclear power plant to operate at full power. So simply increasing the energy level of something, no, that doesn't make it more dangerous. It's all about within its design parameter, being within your design parameter.
But is there an advantage of using AC? I mean, back then, all they wanted was light using incandescent lights, and those don't care about AC or DC. Here I'm running a regular light bulb on AC as usual.
The main difference, I mean, it isn't the end device, it's efficiency of transporting it across long range. Though back then, I don't think they had much of an option as far as high voltage DC transformers. Forget when those were invented, but I don't think they were around in Edison's time period.
And here, I killed it. Don't short. Anyways, with this, I'm converting the AC into DC using it's a single diode, but it will do. And if I measure the voltage at the output...
What? Does he have a history with diodes or something?
Holy the capacitor... Piece of shit. Anyways, I'm reading around 170 volt DC. And although it's still quite dangerous, I can still touch it, and it's not as remotely as painful as touching the 120 volt AC. And
as shown in that previous video we looked at, I guess hands are better than tongues, I guess. Okay.
The light bulb runs on it just fine, and it's even a little bit brighter because it's 170 volt continuous. Beside the lights, the electric motors were becoming more popular in home appliances like meat grinders or fans and such. But even those could be made into brushless AC or brushed DC, for example. Of course, a brushless AC motor like this one that I took from...
Yes, using AC to power induction motors, for instance, are a lot simpler and more efficient than DC motors that have the commutators and the brushes. Not saying you need one for the other, but anyway.
An old microwave oven can last much longer than a brush... Loose wires, avoid them. Anyways, brushes in DC brush motors wear out eventually, and that's why it can last longer. But beside that fact, there doesn't seem to be much preference between AC and DC. But the real advantage of AC is not at home. It's before electricity even gets to home, in transmission lines. And that's why Edison's DC power distribution system eventually died away. Here I made a transmission line using thin wires.
Yeah, imagine like the DC battery powered HVAC or something more complex that didn't exist back then.
Using my supply, I'll
house.
try to place 10 volts across my 1 ohm load for 10 amps of current, and I'm measuring the voltage across my load. Let's try it. See, the voltage is like 7.5. And you see my transmission line is starting to smoke and heat up, and the voltage continues to drop. See, the line resistance is so much that the voltage across the load doesn't even get to 10 volts. It's at 7 volts for 7 amps through the load. And because of the high resistance, it's heating up so much. Similarly, because Edison was passing low voltage across the transmission lines, a ton of current was passing through the lines.
That's true,
and there is a
too.
limitation
Yep.
to how thick you can make the wires.
And that's why losses are less with the higher voltage, because power is current squared times resistance, or current times voltage. So for a given power, higher voltages reduce the current, and current generates a lot of heat. So yeah, not only does it increase the temperature there, but it's just a lot of energy that's not going to powering your house or whatever.
Before they break under their own weight or become too expensive. Huge currents through the resistance of the wire would result in large voltage drops over longer distances. And that's why Edison's system could only transmit power to around a mile or two from the power source. Otherwise, the power loss would be so much over the lines that would cause huge inefficiency.
Yep. So there's your choice. AC power or build a nuclear power plant practically within your house. Because a mile at a nuclear power plant, you're still on the property.
Of course, Edison was aware of his shitty system, so he decided to let one of his genius employees to take care of the problem, who was our beloved Nikola Tesla. He was working for Edison at the time. According to Tesla, Edison promised him $50,000, which was a lot of money back then, if Tesla was able to make great improvements to Edison's DC system.
A lot of money back then, but considering how much that revolutionized power transmission and where we can put our power plants, oh yeah, even back then, worth way more than that.
Which Tesla did in a few months, and when he went to Edison to ask for the money, he said, I was joking. Obviously, you're not aware of our American humor. To which Tesla said, you,
I remember
quit.
hearing about
Later,
something like
Tesla
that.
came up with his genius system and developed it for Westinghouse Company. What he did was to transmit power.
Westinghouse, that was the design of the reactor type that I worked at. It was a Westinghouse 4-loop pressurized water reactor. Interesting seeing how old these are. Of course, in Edison's time period, they probably split atoms using really small hammers.
Much smarter. He used AC so he could change the voltage level using transformers. Here I'll use my auto transformer to generate 10 volt AC, which would result in 10 amp AC through my 1 ohm load. But before I send it through the transmission line, first I'll step the voltage up using my microwave transformer. And then I would step the voltage down after the line if I had a transformer. Well, guess I can borrow the one from our microwave.
Oh.
They're using tamper-proof screws to stop me.
Getting in the
What they
microwave.
don't know is
boy.
that nothing can stop me. They're just postponing the inevitable. There we are.
You'll not stop me from tampering.
I'll just take a picture of the wiring before I pull it out. I don't want to blow it up later. There we are. Okay, now we have both transformers connected. Let's do some voltage measurements before I connect the load. At the input, we have close to 10 volts, so that's good. On the transmission line, we get around 190, 200 volts.
Yeah.
And at the output, again, we have close to 10 volts, so that's pretty good. Now let's connect the load. Okay. And the voltage across the load.
The other good thing about AC, I mean, he covered the transmission and end user side, but just production. Steam turbines that spin AC generators are standard. It's a lot more efficient to generate electricity that way too.
Is 1.6 volts. That's garbage. What happened? The transmission line voltage 118 volts. Everything dropped.
Yeah.
This is worse than the DC system. What's going on, Tesla? Let's measure the transformer's secondary winding resistance. It's around 100 ohms. No wonder.
Can't say I've ever used microwave transformers for transmission.
There's too much drop over the large resistance of the secondary. So these transformers are not made for this purpose.
Right.
That was a bad example. Doesn't matter. I'm gonna transmit power no matter what. 2 volts, 3 volts, 4, 5, 6, 7, 8, 9, and 10 volts across the load. We did it! And our transmission line is not burning, so that's always a plus.
Always a plus. Wonder if he's the reason why we have procedures for switchyard fires.
Nothing is exploding. What is the transmission line voltage now?
I'm just waiting for something.
820 volts! Well, anyways, although this is a pretty bad example, you can see that I'm transmitting more power than the DC system, but my transmission lines are not burning. So
That's good. Now, DC power is also heavily used in nuclear power plants, but for very different reasons. It's used for critical power, uninterruptible power supplies for instrumentation that monitors important parameters such as reactor coolant temperature and pressure, as well as the control rods themselves. So it's a solid backup power. It's not frequency dependent, fast response. And all of that's lower voltage, at least at a nuclear plant. And DC is used because it's less subject to interference. I mean, it's simpler, straight, continuous, non-pulsing. And it's also used in control circuits for that same reason. So nothing against DC power. It's very good at what it does. And you need both to make a nuclear power plant run well.
So that's sort of a success. See, in this system, I can transmit a lot of power, in this case around 100 watts, without having to thicken the transmission line wires. And if the transformers were better, the efficiency would be higher too.
Yeah, that's the the main issue with this example is he's using microwave transformers that aren't ideal for this purpose. But he knows that. It's just an exercise.
The higher you convert the voltage to, the easier it is to transmit power over greater distances, with some limitations of course. That's why in real life they convert it to 10 kilovolts or 100 kilovolts. Why? Because in transformers the input and output power is ideally the same.
There is some that even 500 kilovolts isn't unheard of for like really remote areas, that it's worth the higher voltage just because you're transporting something like 500, 1,000 miles, something like that.
Well, not really, because there's always some power loss, as you saw. And power is voltage times current. So for example, if I increase the voltage by 20 times in order to have the same power, the current has to drop by 20 times at the output of the transformer and over the transmission lines. And because the power through a resistor is equal to resistance times current squared, the power would be 400 times less wasted on wires.
Yeah, glad he brought that up too. That's the big thing. You don't want all your hard invested money on your nuclear power plant to just go away in your transmission lines.
And with high voltage comes great responsibility. The transmission lines have to be...
That's true. Just like with radioactive material comes great responsibility. That's actually a better way of looking at it. Forget the whole one is dangerous, one is safe sort of thing. It's really about training and respect for the amount of energy you're looking for. I like it.
Placed far enough so no arcing happens. There is no easy way to do the same thing with Edison's stupid DC system. In order to change the voltage, you would have to convert DC to AC, increase the voltage, and then convert the AC back to DC, and lose a lot of power in the process. Edison still couldn't see this. All he saw was that his company was losing the contract of his life to power the world.
Uninterruptible power supplies involve converting back and forth, but they're very good at what they're supposed to do, and that is keep your critical instruments online.
So all he did was to grab the fact that Tesla's system was running on super high voltage, like 10 kilovolt or 100 kilovolt, and say that it's super dangerous to people by electrocuting animals with 10 kilovolt in public.
Wow.
Thomas Edison. He contributed a lot to science and technology, but he was also an asshole businessman, and that bit him in the lower back area. The moral of the story, don't be an asshole.
Very well said. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.